Okay, so now we're going to move on to our research flagship session, talking about research flagship projects 1 and 2. And I'm going to turn the floor over to Frank and Mary for that, for this session here that'll take us up to lunch.
There. All righty. Thank you. Oh, no, go ahead, Mary. All right. Well, research. It's a big part of SpectrumX. Many of you have contributed and are continuing to contribute. I'm Frank Lind, for those who I've not met in person. I'm Deputy Director for Research. This is Mary Knapp, who's our Flagship Project Manager and general awesome experiment planner and executor, because without her, none of this happens. And we don't, but it's also without, the team here. So I want to say I was a little overwhelmed, and I was trying to make this a short talk. And I asked everybody, of course, I gave no deadline for getting these slides to all our work element leads. And thank you, everyone, for being patient. They gave them to me, like an hour before this, or 2 hours before on average. So I was rushing to get everything included. And I'm a little overwhelmed by how much we've done. And so this is going to go a little longer than I wanted. And I'm going to hand it off to Mary, and she's going to lead talking about our flagship experiments, what we've done, and what we're planning to do this summer, which is going to be really exciting. So we have a number of ways of organizing research. We've got the flagship projects, the research communities, seed projects, liaison projects, and we've put a huge amount of effort into pivoting to create these coordinated flagship projects. It's showing results. The center research, we've got a lot of researchers and graduate students engaged. The poster session yesterday showed how much everyone is doing. And it's always just a subset of what people are working on. There's been a lot of research memos written. For those who are work element leads, I want more memos. We don't do enough of them. It's good scientific practice. We have a bunch of GitHub repositories, many of which are public, some of which are still private. And then we've built mobile experiment platforms, which everybody is talking about because they're very tangible, and they've come such a long ways from when they were, like how do we get some data systems in the field yesterday, right? Flagship projects have been significant investments for us that focus efforts on really policy-driven research priorities. They're not just, me coming in and dictating things. I have my influence on stuff, and Mary's had her influence. But the Research Planning Committee and the Center Workshop, we've had a process of gathering people together, getting ideas put up. Everybody gets like a slide. We actually rate and discuss the different things. And then there's a process after that of trying to organize common ideas and themes of work into really, things that are a coherent whole. And so there you'll see that they've got themes associated with them. And those themes, as it's turned out, have been pretty well on mark for policy. We set out, guided by the National Spectrum Strategy at the time, in order to try to select what we were doing. But of the things we could have picked, we picked things that were both achievable and that were on target. And so I'm really happy about that. We also have very active and involved project management between Mary and I and our work element leads. People have been really keeping coordinated and showing up at the meetings and reporting. And we've also been driving incremental progress with a lot of workshop activities that get people together for focused things. Like we just had a software radio workshop at University of Colorado Boulder. We had this recent experiment at UW-Madison. And those are very focused, overly intense, short notice activities that drive people to kind of achieve things in short time. It can be a little painful. It can be extremely stressful in the field for people, and we kind of try to mix some fun in and some good things. But underneath it is about driving progress on stuff, and you don't get that sometimes without a little bit of pressure. Now, our first flagship is Spectrum Awareness for Coexistence. That's its real, full name. It really focuses initially on the 7 to 8.4 gigahertz band. We kind of list that as lower 7 now. I'm actually not supposed to have OBBBA up there anymore. That's politically verbatim now. I'm supposed to have something else. I can't remember the alternative political name. And this was to try to really put together both, I think, are infrastructure components for measuring spectrum and analyzing data, as well as to organize things around a series of intensive field experiments that would provide really unique experiences for students. So, where a lot of our educational activity has focused on secondary schools, undergraduate education, we had to focus here on trying to tie in the senior undergraduate and graduate experience with an understanding that the flagships by themselves aren't a full graduate student project the way they're structured. They can be part of it, but the graduate students are going to have to go beyond it in various ways. And the underneath it is to do measurements about this lower 7 gigahertz band, and that was selected for policy relevance. And as it turns out, the government decided to reallocate this band mostly to fixed wireless. And so, this is still ongoing. We haven't seen the final results of that. But our research was leading into this, and we were among the first making measurements on the ground, whereas even the government agencies that have been asked to look at this are still playing a little bit of catch up in some areas. Now, we also think about this from an infrastructure point of view as spectrum sensing is scale. How do we build the combination of hardware, software, people, infrastructure in order to be able to go out, make measurements, get them into a common place where we can actually all work with them, do analysis, and then get results out that are either policy results, science results, technical advances. And this was all about creating a process that started with our mobile experiment platform and really our Radio Hound platforms, went through with software control, organized it into the Spectrum data system that you've heard about already and maybe seen one of the demos on, as the place to aggregate information. And really that's about getting it so that you don't take data yourself and keep it in your own little silo. You take data and make it available to the entire team or to a larger team or even the world, and you have people work on that data and do things with it. Because when you can take a lot of data, and data by itself doesn't mean anything, okay, you actually have to produce meaning from data. And that's the important thing that SDS is about triggering. It's about removing the barriers for people getting access to high quality experimental measurements. It has a bigger vision down the road I might talk about tomorrow a little bit. Now, our timeline. We set an aggressive timeline coming out of the pivot. We really had 2.5 years left in the center when we started to pivot things. And really by the time we got going, there was 2 years. We started with some requirements planning. So what did we want to do? How are we going to achieve it? We organized people into working elements and working groups and work areas and teams. And then we really rolled through with starting to execute. And we aggressively built the maps. The maps were built with rapid prototyping on timescales that are not timescales you normally do projects on. We really had the CAD designs in a couple months, and then we went within a couple months to a workshop where we had students build them. And we learned a lot. We learned that if you tell someone to turn something until it stops and it mechanically can destroy the thing that you're turning, it won't stop. And so that was a valuable lesson, and it improved our instructions. And it also taught us, to be a little more careful of what we put down in those instructions. But nevertheless, we got first light at that workshop, and that was incredible. And we've gone on to that and greatly improved things and begun to really deploy stuff. And you can see these things. This was a slide that I put up right at the beginning. It was a timeline. And we are checking off systematically thing after thing after thing on here. And all the ones that have the little timers on them are actually really far along. And I'm going to be happy to talk about some of the progress there. But so, at the end of this, I kind of have a vision that we're going to have a report. And that report might come in year 6. That might be one of the things we do. But, I'm really proud of everyone's efforts to actually do this, because it's been kind of an incredible ride to see things go from concepts and ideas all the way to physically realize things that they're starting to have really amazing impact and result. Now, I got to say, so John apologized when he sent me this slide, and I got to say, I really like this slide. John, you'll see later that I really like this slide. All right, so mobile experiment platform, this is what's new, okay? We've been using it. Okay, so that's the most exciting thing, is data systems that you build in boxes. Like I built a lot of software radios in boxes over the years, some of them in big boxes and racks, some of them in littler boxes. If they're not out collecting data and you're not doing something with the data, it's a radio in a box. It's not much better than a paperweight. Okay, it's a big paperweight. You can hold down a table with it in a hurricane, but nevertheless, it's something that you got to go use. And so I am excited to see everyone using these systems, and I want to see a lot more of it. And this summer, we're going to make that happen. We've got improvements that have been driven by our team in a lot of the work. Randy's done incredible work on the user interface. John has done a lot on knocking out bugs and problems that are behind the scenes that you would not like in your data. And some of our data, unfortunately, has them, those bugs. But nevertheless, they're understood now, they're fixed. So the team has done a great job on that. And there's been a lot of improvements in documentation. Raphael is working on duplicating a MEP independently, working from our GitHub and documentation with the MIT team. And so we're trying to make sure that it's actually possible to replicate these. All right, and that's going to lead to them being openly available in public, and that's going to be exciting. Mobile experiment platform, we've built 12 of them. We've used them in the field. Students have become engaged and learned about them. You can have a lot of fun with the MEP. You can make actual scientific measurements with the MEP. And really, the level of performance available in the platforms, we've only just touched what can be done with it. They're very, very capable radio and computing platforms. This is, of course, what one looks like open. It's got performance characteristics. It's got some targets. We're almost to our bandwidth targets. We're very close. Ryan hasn't benchmarked how fast we can actually go. We've just got we've gotten things going pretty fast on RF recording. We're working a little bit on the transmit side. It's not quite where we want it, but it's really gone well. And there's areas that we know we want to improve, like the power subsystem, and that's almost off the shelf. I wish I could buy the industrial version of what I'm using for another project, because it would be perfect. But sensor control system. This is an area that from the beginning of the MEP to now has made extraordinary progress, and it's really integrated many of the ideas and concepts from the RadioHound software in with the MEP. It's reached the point we're configuring MEPs uniformly. We're getting data loaded into SDS. We're controlling a lot of the complicated hardware and analog systems and RF systems directly from the GUIs. And it's streaming data, and it coordinates, and it's all mosquito messaging based. It's awesome. All right, so this is like the ability to control sensors, and controlling one sensor is a good thing. Controlling 12 sensors starts to be pretty challenging. The next generation of this, as we look forward, might be controlling hundreds and thousands of sensors. Right? You need solid infrastructure to even start that process, and so we're really looking forward to the future of that. And I'll talk about that later a little bit. This is what the user interface looks like. Go to Randy if you want to see live stuff and play around with it. We can make that happen. Flagship experiments. All right, so we've run a number of experiments. This is the list. We've checked them off. We're down to our remaining planned experiment. And those who've been here a little bit will notice it's not the planned experiment we planned on. Right? So planning is great. It's essential, and plans are not always what happens when you kind of encounter the enemy. I know who the enemy is, but I'm not going to mention them here because it's not going to go over politically well, so I won't. But nevertheless, we had to pivot from our original plan of Wallops Flight Facility. I think down the road there may be possibilities of working with them to do this. The team there on the ground at NOAA and NASA are great, and I've had a lot of support from within both agencies to try to make this happen. But at the end of the day, we had to pivot. And so our backup plan was always, well, if we really have to pivot, maybe we'll do something around Haystack, quote unquote. And we can mock up the Westford telescope to emulate SATCOM. We can do a lot of things. And it's really, from my point of view, not just about being around Haystack. It's about kind of the New England experience, right? So we're going to have to come up with some good things and good experiments as a team. And so Mary's going to talk a lot more about what we're thinking about and planning and what we want from everyone. But at the end of the day, tomorrow in the morning, those who are able to be there here in person or virtually, we're going to really plan this thing and write the experiment plan. That's the goal, is to get that outlined so that Mary, myself, and I guess Randall, it's Randy in the back right there, he's going to be helping us with this planning, logistics, and execution on this. And we're going to go to town. Okay, so this is going to be an awesome experience. And I want every SpectrumX group to be part of it, but not just by yourselves. You don't get to do projects by yourselves on this one. It's got to be teamwork. All right? Now, we've been working a lot about next generation rights and policies, our groups. I'll apologize to everyone. I took all your names off everything. This is a big team and effort, and you know who you are, and everybody knows who you are largely. But if you want the details, you can talk to the appropriate groups and people, or talk to me, and I'll point you at the right people's. But next generation wireless and policy, there's been a lot of work on understanding what's going on, evaluating the guidance and providing guidance for the experiments on what might be impactful on particular things and approaches that we may want to test. This is all going to come into this next set of experiments. It's no longer just about collecting data. It's about collecting data in the context of policy and rights approaches, all right? And, sometimes we're going to have to mock it up and fake it. Sometimes we're going to have to use secondary systems to coordinate that. We might not set up a full zone management system, although maybe Utah, Powder, we can manage to do something like that. But nevertheless, we want to be able to emulate the behaviors of the systems using these approaches. We've got a lot of work that's gone into design, modeling, and analysis of beacon signaling and coordination. So yesterday you saw Lee put up the waveforms used at UW-Madison, and off to the side of the 6G, 5G transmissions is a radio beacon that has a particular set of structures. There's really a carrier to allow you to lock onto it. There is a metadata stream that tells you what's happening. And then there's a propagation measurement stream that's modeled on what the radio amateur community does with Whisper. So this has been paired with analysis at a high level, both mathematical and theoretical, of how systems can be protected using beacons, how you can coordinate systems using beacons. And so a lot of the ideas and developments that have come on the theoretical side, we're now in a position to go test. Okay, and I've emphasized to the teams I wanted testable predictions, even if they're prosaic, even if we think we know that's what's supposed to happen, there is a value in science to replication, all right, to duplicating and verifying before you extend things. And in some cases, you go into duplicate and verify, and you find that there are edge cases or things people didn't consider, and you make discoveries. So that's the model behind this. We also, of course, are looking a lot at how to share spectrum in 7 to 8 gigahertz. And, there's different approaches for incumbents. There's different rights approaches. There's different kinds of things that you think should happen if you have certain behaviors, like back-off windows, for example, that are shown here, can have different behavioral impacts on how long it takes to complete data transfers, for example, or the reliability of your data links. So we want to go in and actually make experiments that allow us to evaluate various portions of these kinds of predictions. We have tools that we've been building to do this. One of the really exciting tools that's come a long way has been worked on by the Colorado group, and we have a phased array demonstrator for 7 to 8 gigahertz that's really showing real physical hardware, real world testing and results. And we're hoping we can get this out in the field and actually make that happen. And I know, Layla, we need to talk about funding to do some of that, but we'll work that out. And I think that underneath this, there's been a lot of work with this with nulling. And one of the things to realize about 7 to 8 gigahertz, and that was the motivation behind the array demonstrator, is future systems deployed for next generation wireless in this frequency range are almost certainly going to be all phased arrays. And so to actually do credible experiments, we actually have to be able to emulate that, at least at a reasonable level of fidelity. Now, we're not going to go out and build a 1,000-element array under the SpectrumX budgets and approaches. We're building some smaller things, but it will allow us to look at dropping a sector null on something or trying to drop a narrow null on things. It will allow us to quantify which things are performant and which things maybe aren't for, say, protecting a SATCOM system or having a satellite base station near your cellular tower. The satellite base stations actually transmit. They, in the lower 7 gigahertz, are transmitting in that band. And if you put a cell tower near them, it's actually the SATCOM that's going to jam the cell tower and cause intermittent problems. Now, maybe that can simply be solved with array processing, and they just drop a null on it, and it all works. Maybe they have to have a larger distance from the SATCOM station. But that gets into how big does, say, an exclusion zone need to be around a given satellite communications center. And so that's important for people like NASA and NOAA and others in DoD who are operating these systems. And having coexistence approaches gives people and regulators the toolbook to allow us to have good spectrum management and approaches that are good for maybe win-win for all parties. We have our spectrum data system. This has really revolved into a thing where data now goes in. A lot of the early teething pains were painful. I know I had to pound on people to get the data into this for some of the stuff. There was a real desire to just exchange hard drives. I understand. You got to get the research done. On the other hand, it's important to create this larger federated approach of immediately visible and available data. Now we have constraints on visibility that we can control, like access control, so that sensitive data doesn't just automatically go in the wild. But on the other hand, in the future, we can imagine this type of system evolving into something that's real-time, ubiquitous, and you really can know what's happening with spectrum very easily in the world. Now, underneath this, we've leveraged a lot of this in workshops and engagement to really build community and training and to provide unique experiences for students. I'll tell you my favorite moment from the MEP workshop was one of the students came up to me, and she was a young woman, an undergrad. She was at our workshop to build this mobile experiment platform. And she said to me, "This is really exciting. I'm in engineering and I've never built anything before." And I was like, oh man, okay. And this was her first opportunity to physically build a real piece of radio instrumentation and work with it. And she learned a lot, of course, because there's always a lot to learn, no matter how many times you've done this. Talk to me about my son's project if you want to know how painful this can be. But nevertheless, I think that this community development aspect of bringing people together, creating kind of, somewhat artificial, intense situations that nevertheless have real meaning, real merit, and have people and mentors there that can engage, who have the requisite experience, has been really powerful for us. And we noticed this, and so we started to do more workshops, and I think that that's going really well. And I think the experiments are a type of thing that has that similar value. It's also, from a workforce training and development point of view, what will really catch the eye of an employer. Oh, you worked on real hardware. You went into the field and took real measurements. Where did you go? Oh, it was the VLA. Wow. It's not something every candidate that walks into a job interview at a cellular company or a wireless technology company or the Department of Defense or even at the NTIA is going to have as a set of experience. And when you talk to the agencies, you talk to the folks at ITS, they get somebody coming in and it takes them 2 years to train them. If we cut that in half, we've created an immense value, for example. Now, I couldn't be outdone. Sorry. All right, we have a lot of results for Radio Hound X, and it's not quite there, but it's awesome, and I wanted to highlight that. And so I asked Jim, and I love AI and I hate AI, so it's not like a two-way street for me. But I asked Gemini to do some illustrations for me on various things here. So, and I really, this came out of just a query about SpectrumX and Radio Hound X, and I thought this was awesome. So there we go. We're going to talk about Radio Hound X now. So where are we really going? This was it for our flagships, the longer-term infrastructure vision. All right? The MEP, as wonderful as it is, from my point of view, is technologically 15, 20 years behind. All right? We did a great job on it. It's high technology readiness level in NASA speak, okay? It was ready to go. We did it quick. We got it in the field and we're using it. Sure, there's integration challenges, bugs, software, but part of the reason we're able to make it work is that all the stuff in it is pretty close to ready to go. Radio Hound X is not ready to go, okay? This is the big picture concept. And you'll notice I put visions of little antennas in glass bottles. Actually, Gemini came up with this prior to one of our meetings about 2.5 years ago when I asked it to visualize something like this, and it was not what I was thinking of at all. And it was very clever, and so I've kind of run with it as a concept. But underneath it is something I've talked about for many, many years called drop and go radios or sensors. And the idea here is if you look at the specs on the right, it's kind of a wide frequency range EDIS radio, but you don't want to have the external computer, so the computer's integrated. And the power envelope it needs is unreasonably low. Okay, I want to do this in sub 10 watts. I recently had a platform I was doing radio in with sub 10 watts, and it's really exciting because you stick a good battery on it and it runs for 24 hours. And you stick some solar panels on that and it runs continuously and doesn't stop. Okay, so that's very exciting. That changes the deployment logistics. And logistics are the pain and the bane of measurements, period. Okay, we see that in our experiments. We see that in trying to put sensors in places. You have to have incredibly efficient logistics and low cost and high reliability to actually field large numbers of sensors and get them to work. Either that or really, really big budgets, but we'll see. We'll work on them in DC, right, Nick? So underneath this is a vision of an ASIC, okay, or an ASIC multi-chip module or something like that. It's I've done enough of this. I know some stuff about it, but I haven't done enough of it to be an expert. The big picture thing or the little picture thing in the corner is the RTL SDR. Okay, that revolutionized software radios and made them available widely to the general public. And it was intended as a TV dongle, okay? It was produced to receive European television. It was made by an Asian company and pretty much a very small team. And I heard that the ASIC designer was just one guy, and he wanted to debug stuff. And he put in some debug features in the ASIC that someone discovered and hooked into GNU Radio and made a radio out of it. And all of a sudden, it was the least expensive software radio. And it was like a $15 software radio that you would plug into a $1,000 computer. And if you wanted to put it outdoors, you'd add $500 of logistics. So it was a $1,600 software radio. But at the time, that was an order of magnitude cheaper than everything else. And underneath this is the idea that we might be able to do this, but also get rid of the logistics. And this wasn't made for spectrum sensing. It's got a lot of stuff that from an RF point of view is kind of crappy. We can do a lot better than this. And we can do a lot better at the signal processing. And we can create something that is incredible if we can continue to dig after this direction. Now, we've been making progress. Sudhakar has been working very hard with his students to look at building an ASIC tuner that covers, the goal is to cover up to 18 gigahertz. I'll show you some results from the 5.6 gigahertz unit, and I'll show you some of the stuff that's leading to the 9 gigahertz unit. We're kind of taking this in steps because it's hard to make the ASICs work in one go. They're very complicated. They take a lot of resources and simulation time. But the idea is to really kind of transform the space, weight, and power associated with these integrated radios. And there's been some work in progress on doing this using these architectures that are time varying periodically, modulated filters essentially, and it allows you to down convert with good dynamic range using kind of a lookup table based architecture for the local oscillators. That's very interesting. And so underneath it though is to try to do this in really something that's 5 or 6 times better in space, weight, and power than the current state-of-the-art ASICs. So we're not just even targeting being as good as the current state-of-the-art ASICs, we're trying to do significantly better than them. Now, this has progressed to actual measurements of some of their early devices, and the early devices, on the left is the simulation, on the right are the actual measurements, and you're starting the really narrower band systems are coming in at under 100 milliwatts. All right. Just as a reference, I'm doing a conventional tuner, and it's going to be about 8 watts a channel to do that conventional tuner. The whole architecture can't fit in 10 watts when I do it with conventional techniques and circuit board design and local oscillators. And I'm using marvelous chips from TI and Analog Devices, things that are incredible. If you told me a decade some of these things would exist, I would have laughed. I mean, I would have thought, no, there's no way. So, we're using state-of-the-art things and still coming in orders of magnitude higher in power. The 5 gigahertz tuner prototype was taped out, brought back, and is being tested. They've got actual real-world measurement of filter responses, noise figures. It's being tested with the Xilinx RFSoC as kind of the test bed for it. The 9 gigahertz tuner is in ASIC layout right now. They're getting close to being able to tape out. The lower right is a simulation of the dynamic range achievable with this tuner architecture, which that filtering dynamic range that's shown for doing that in this small space with this kind of technology is actually absolutely amazing. And the projected power for this 9 gigahertz one is like 300 milliwatts, right? So you're starting to get into power regimes that are going to get us in that sub-watt territory for the analog. The digitization can be done sub-watt already. That leaves us with an important thing, which is the computing. And I know we've got the Florida group, Arjuna, who I think is here somewhere. He was here earlier. He's been doing work on the ASIC signal processing. So one of the things is our bane right now in software radio and radio in general is that right out of the analog and the digitization, now you got numbers you got to deal with. You want to do mathematics on the numbers, right? We like digital signal processing. We like AI ML now. We're going to do all this math to the data. The data bandwidths can be incredible. I mean, it's not just megahertz or tens of kilohertz or something like that. We're, even in Radio Hound X, we're targeting hundreds of megahertz of bandwidth. The MEP can digitize at 5 gigasamples a second a channel if you wanted to. It can put out so much data that you don't know what to do with it. You can build very high power data recording. It takes energy and compute to deal with this information flow. And so to do that, we've had an effort going on to look at how to change the signal processing that goes with this. And Arjuna and Sudhakar spent a lot of time looking at reviving analog or proximate processing for Fourier transforms using more modern ASIC approaches and technologies and processes that are available. And this has been prototyped into a analog or approximate discrete Fourier transform that has order n complexity in it instead of n log n. So it operates with fewer computational cycles to get the same result as the FFT. It's not perfectly accurate to the FFT, but it may be good enough for our spectrum monitoring. And then he's combined this into a polyphase filter bank architecture to allow us to actually get wider bandwidths and channelize them so that we can analyze them efficiently and effectively. And so the 32-point ADFT, he's got the architecture for it. They've been prototyping and simulating in MATLAB, generating it as IP blocks for Xilinx AMD systems so that it can be tested in actual hardware. And then he's put this together into a uniformly decimated polyphase filter bank, what's interesting is this polyphase filter bank approach is what astronomy spectrometers do in order to get good interchannel rejection, okay? So it's inherently a very good approach for radio spectrum monitoring. Now, FFT, as I've told other people here, is only one transform. One can imagine extending these kinds of approaches to other kinds of transforms, whether it's radon transforms or wavelet transforms, right? There's different ways of viewing the universe with the filters we put on it. And the electromagnetic spectrum and the digitization of it is all about filtering, it's all about signals, and it's all about what you want to find in it as much as the techniques you use to get there. So that's been going on. This has been tested in a loopback mode and is showing actual channelization. So we're getting quantitative results. And really the next real step for this is to try to realize these in an actual ASIC. And the associated power levels on this are orders of magnitude lower than what you get in, say, a pure Xilinx chip if you do this in ASIC. So the idea is ultimately that we could have low-power CPUs paired with low-power analog signal processing paired with the ultra-broadband tuning low-power radios, and we really hit sensors that are in maybe not even the sub-ton watt level, maybe the 1 watt level, okay? How much spectrum sensing can you do for 1 watt, and how many of them can you make? For comparison and testing, we're building a slice architecture for RadioHound X. This is actually, they're in schematic review and they're in layout right now. This is a carrier board in the lower right that'll go with the MEP, so we can use these cards with the MEP. In the upper right is a test card that's kind of the reference design. I have a 3 to 18 gigahertz tuner card that's about to be ready for schematic review, and we're going to get these going over the summer and fabricated in small quantities for testing. The other thing we're going to do is we're going to build cards for pseudocars ASICs that allowed us to put the ASICs on these carriers, and we're going to build integrated software radio backends that aren't the carrier for the MEP, but are self-contained MEPs in a little box. And you can see, if you know how big the MEP is, that goes down where the tuner is in the MEP. And so these cards, they're about this big. They're based on slice architectures that have been common in Xilinx chips and in Edis radios for a long time. And we're really going to be able to use this to leverage to build kind of a series of prototype radios and then ultimately evolve those and compare one-to-one the power performance for similar use cases. You could imagine one of the reference design radios in the lower right corner in one mounting slot and pseudocars ASIC in another mounting slot taking the same data at the same time, for example. The high-level architecture for this looks like a MEP on a system on module. All the parts are high TRL and available. They're very high integration. So this is a very challenging set of circuit boards to make. But nevertheless, we're well along on putting this together and bringing this to fruition. It's taken a little longer than I wanted. Now, Flagship 2. We have 2 flagships going on, and scientific coexistence in the high frontier is a very exciting one. We had to be very limited in all the things that we wrote down that we could do, and we down selected to a small number of things that we would do. And nevertheless, the area we picked was how do scientific systems coexist? What are the impacts of mega constellations on them? And what can we do for the future to make these things actually work together? Mega constellations are a reality now. They were only half a reality when we started this. They've launched that many satellites since then. And it's all enabled by exponential decreases in launch costs, brought around first by SpaceX landing rockets and reusing them over and over again. And soon it'll probably be Starship launching things in much larger volumes doing the same thing. So it's timely and relevant. It's timely and relevant from a policy sense. We've had a number of FCC notices of, well, it's really, they're NPRM kind of discussion requests at the moment, and they're probably going to go to full rulemaking at some point, about satellite spectrum abundance, about rules for unleashing space innovation. This is a national area of prioritization, and one of the consequences of this is that these satellite systems are going up so fast that there will be impacts, and there are impacts already. And there is a big question about what can actually be done about such impacts when they're already at scale globally, all right? And we've done simulation, you've got rockets that'll chunk out large numbers of satellites in a hurry. It's the beginning. We are at the beginning of the exponential, not the end. Now, here's my timeline I put together for this. One of the things I'd been critiqued on was I didn't have a Flagship 2 timeline, so I put together a Flagship 2 timeline. And I actually had Google generate what it thought we were doing in the background, and Google Gemini actually knows a lot about us at SpectrumX. It's kind of scary. But then again, all our slides and everything are in Google, so in Google Drive, so that probably is part of it. Nevertheless, we've got kind of a lot of work that's gone on radio development and modeling. We've got ground measurements and harmonic measurements, and a van we'll talk a little bit about that's been under development. A lot of work on looking at Starlink. And then there's been ongoing work on rights and policies and weather forecasts and impacts. What's been going on there, everybody's been making progress systematically on this. And in particular, I'll talk a little bit about the weather impacts. RiskSim, you probably got to see the poster and some of the demos. It's really cool. It evolved out of work we did at MIT, transferred to Notre Dame Research Computing, and DK and Paul have really taken this and run with it and evolved it into something you can go download and use, and or even contribute to if you find you want it to do something. We're gradually evolving it to be more complete and to have better models. The thing we do really, really well in this is handle antenna patterns and geometries between the ground emitters and space emitters. And so that's something that underneath it is, a lot of people make a lot of approximations on, and this was done very systematically and mathematically in a rigorous way. We have some scenarios we're developing for RiskSim. There's really the radio telescope scenario of looking up, focusing from a radio telescope point or set of points on Earth, and then the looking down scenario, the weather satellite radiometers that are critical for things like hurricane forecasts, being able to model those effectively and look at what the perturbations are to their measurements from various emitters that might be, say, 5G on the ground or Starlink gateways or other things in the future that we might want to simulate and model. All of this is done in Python, kind of Jupyter Notebook style. It's very approachable. There's lots of examples. So one of the things that Paul and DK did absolutely well was they went through and made a lot of really nice examples about how to dig in and do things with this simulator. So the use cases for this go way beyond what we've done, and there's many things that can be added, and we have a proposal in to do that, and we'll see how that fares. Okay, I'm going to skip that. The weather modeling, is very important for us to understand what the impacts of all these new systems and emitters will be on systems that are critical to life and safety. And one of the things that really impacts people is our ability to forecast extreme weather events. And hurricanes are a great example of that. It's not only hurricanes. Accurate forecasts allow people to evacuate the right region. They allow you to protect hardware or systems that might be endangered otherwise. And if you don't have lead time, it can become impossible to mitigate or prevent damage or move people out of a dangerous area. And so, the fact that we're deploying radio systems and they have bands and, they're sometimes even adjacent to bands that are used for weather radiometers, which are very, very sensitive, it can be very problematic. So we've been looking at how to model this, both with numerical weather simulations. We've got kind of 3 experiments. There's a control experiment. There is a full data denial experiment. So we're using actual data from weather radiometry satellites, and do a run, you don't do anything to it, you make a forecast, and then you do another run, and you turn off all the weather radiometer data and you see what happens. And then we're in the process of doing a final run, which is where we put in a pseudo-realistic model of what a ground emitter set might look like to these weather radiometers, and we see what the impact is. And so these simulations actually take months to run. So they're full supercomputer numerical weather predictions. And the team at University of Wisconsin-Madison SCCC has been working on this, and it's great that we kind of worked that out, and then they've gotten involved with all these experimental projects, and so it's built kind of an interesting relationship that might not have otherwise existed. There's been a lot of work on verification of the NSF data and the modeling against operational analysis, and then looking at forecast predictions in the Northern Hemisphere, the Southern America, North America, the tropics, and then trying to understand statistically in the numerical weather outputs whether what we're doing from a radio point of view to the weather radiometers is impacting them or not. And so there are, with the data denial case, you turn off the systems and the forecasts don't do as well. Okay, and that's not a huge surprise, but at some level quantitatively showing it and showing how much is something that there hasn't been a lot of work on. And we talked to one of the groups in Europe that also does this, and they tend to focus on specific cases and very long time frames. And so for us to put together something where it's possible for us to really go forward and do this systematically, at least in one use case that's interesting, is hopefully setting the stage for doing this on a larger scale much more systematically in the future. There's weather outputs that come out of this, of temperature and pressure. So often you're actually representing the atmosphere as pressure levels, because those are geophysically more constant than altitude. Pressure at a given altitude varies, but if you have, what we're really doing is having altitude vary here. But from a weather modeling point of view, it's the pressure field that matters. And then there's temperature field, and you can look at where the anomalies show up and the root mean square errors happen for the full data denial case. And then you look at the anomalies in the forecast skills, and they have a quantitative metrics for how much your forecast is degrading as a function of time and how your uncertainty is going up. And one of the things that's interesting about this is the numerical weather models take a lot of data to spin up and stabilize. Then you perturb them, and then they actually show effects much farther in the future, more strongly than you'd affect. So that error that this seems very small initially propagates forward into your future prediction and becomes larger and larger and larger. And so we're seeing that behavior in the degradation percentage and forecast skill as time goes out. And so, data denial certainly has this case. We'll see what the actual simulations where we do much more controlled, more realistic scenario looks like. And there's a 3% one. This prior one was Northern Hemisphere. This is Southern Hemisphere, for example. So actually South America is going to take it worse from our use of radio in forecasting than North America, which is interesting. Now, Wright spectrum models, we've had a lot of work within Flagship 2 looking at different ways of protecting scientific systems. This is Google's visualization of our rights and policy research, and it was awesome. I was absolutely stunned how close this came out conceptually and just like a visualization. So kudos to the Gemini team reading through all our materials in Google Drive. Receiver rights models, interference protection, landscape rights models, where you lay things out, applications-based models where you share spectrum by use and slice. We're looking at all of these as approaches to how we can coexist in the future. And it's going to take all of them, to be honest. Different things are going to be a little different. And a lot of the work in looking at this, at these, say, application-based rights models, what can be tolerated, what can't be tolerated, every type of scientific system is a little different. They're not all amenable to just one way of protecting science. And that may be unfortunate because it makes the political process and problem harder, but it's also maybe we have to maybe look at it as an opportunity to be inventive and create frameworks that really allow us to incentivize people and commercial applications of the spectrum and military applications to really harmonize in a way where we can get some way of coordinating our scientific instruments and systems. And so we really can't have a one-size-fits-all approach. Going forward a little bit, we're looking at what we're going to do with data collection and radio coexistence measurements for this also. This is a data Gemini visualization of us making measurements and, for FP2 with Starlink satellites, so I really like that cartoon. I thought that came out great. We've done a lot of modeling and measurements. The Westward results have been very interesting in the X-band lower KU band. This is now in review, but we show interference in the radio astronomy band adjacent to the Starlink downlinks. So, and that's quantitative and statistically significant and absolutely calibrated data. We have also looked at the 1420 megahertz band, where we found unintended electromagnetic radiation that statistically has been shown to be clearly essentially in violation of ITU protections for the 1420 megahertz band. So we're showing actually policy relevant things. There may not be things that people want to hear, but we are seeing already from Starlink and other satellites, not just Starlink, OneWeb, actually some of the Russian satellites. We already see emission levels that we don't understand why they're happening. They're not controlled. You're not going to use beam avoidance to get rid of this. We may be able to find out why they happen and shield the satellites or the electronics. So it's not that it's not amenable to correction. It's just something that we actually weren't aware of, and it takes very sensitive instrumentation to do that. But then again, what we're protecting is probably the most sensitive radio instrumentation in the world, right? And the most sensitive instrumentation people are planning to build. And so this is really compelling, and this is some of the statistics where we looked at full data versus satellites. We've been very systematic about working to remove other RFI from the data and to kind of get clean baseline cases versus clean cases with satellites involved. And the statistical analysis is pretty clear that there's significant energy off these satellites. For radio astronomy, now, and it's above the ITU thresholds, it's not strong. It's still, from a communications perspective, it's almost imperceptibly weak. We have been working to bring capability to the 37-meter antenna so that we can hook some MEPs up. This summer, I think this is really going to happen. We have other capabilities at K-band, Q-band, and W-band that we're going to look at what we can do in terms of spectrum monitoring, collecting some data. MIT RU students, I'm looking at you. There's going to be a lot of fun to be had. We've had teams, Maria has been looking with her students at harmonic detection and measurement. This is something that ties in potentially to the Haystack measurements. We may be able to go after Starlink harmonics for real and get you real data off the mega constellations. So that'll be really exciting. And there's been a lot of work on the AI ML kind of identification classification framework to go with this. So feeding this real world data in significant amounts is going to be exciting. Maria's already done some really great stuff getting at data from GBT and trying to protect that system. But we can really expand the data sets for this in an exciting way and do nice stuff with it. And there's been a lot of harmonic hunting in the wild. We can do this with MEPs in the field also. So that really, when we finish the prototype 3 to 18 gigahertz tuners, is really going to be something we can go after with MEPs in a very serious way. So looking ahead a little bit, there's a lot of opportunity for this. We've had a lot of work working on hyperspectral band survey, instrumentation. This is finally kind of coming in a van to fruition. It is serious hardware. It is, mobile. And a van trip is planned. It is almost past its acceptance testing. We got a couple more things that have to get done. And I'm hoping we might actually see this out by Haystack this summer, so we'll see. So I'm not going to really take questions right now. We're going to hold them and go over to Mary real quick because I'm a little behind. But we'll take questions at the end, all right? Next set of slides, please. Thank you.
Green button, right?
Green button. Well, once they bring up the slide back.
Oh, you're too short to see it from over there.
I know. Here.
Okay, maybe I can just do that, and then I can actually see what my slides are. Otherwise, I have to look over there. Okay, so Frank introduced me, but let me just say I'm Mary Knapp. I'm project managing for the Flagship projects. Many of you, I think, know me, and if not, I hope to get to know you. I'm at MIT Haystack. I'm a research scientist. And we're going to talk about experiments. So let's see here. So this is sort of an overview slide of some of the challenges that we're trying to address through SpectrumX work, and particularly our experiments. I'm going to go a little quick because I want to have some time for discussion, so if anyone wants me to slow down, just raise your hand. So this is an overview of the experiments. Frank already showed this slide. We're going to go over each of these just briefly as a recap, and then we're going to talk a little bit about what we're going to do this summer. Okay, so the first workshop we had was at Haystack, and it was about building the maps. How many of you attended that? Can I see hands? Yep, good, good. So this was a really interesting workshop. We were physically building these map platforms. We ran into all sorts of fun challenges mechanically. Once we got them built, we tried to do some sort of first light radio measurements, and we encountered more fun challenges, some of which we solved then and some of which were solved later. But I hope for the folks who attended, this was a good experience. It was a first introduction to the maps, and I'm glad to see many of you here. Let's see. Right. I think this is data systems. Yes. So I'm going to go quickly through this, but we have developed a lot of tools to help us view and transfer and analyze the data that we're collecting. Shout out to the SDS team for a lot of work on making the data accessible. Wait, say hi. Yeah. So if you have any questions about how to get access to the data that was talked about yesterday in the data blitz, or the experiment data that we've been talking about here, go talk to that corner of the room. Okay. All right. Right. So how many of you got to go visit the map in the poster hall? Good. 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 I will also encourage you to attend the tutorial after lunch. Yes, after lunch. Randy is running that right there. So if you're interested in this platform, if you haven't used it before, or if you've used it but you want to learn a little bit more about it, please see Randy for the tutorial. I think that will be very helpful for folks. There have been a lot of improvements in the interface to work with the maps since the very first workshop that we had. So definitely go check those out if you haven't worked with a map since that first workshop. Okay, so as I mentioned, we're going to go through our experiments to date and our future experiment. So our primary goal is to work in this lower 7 gigahertz part of the band for policy relevance reasons. So we tend to stick to that. That's where most of our work is for Flagship 1, and that's what these experiments are related to. We want to look at what the future might look like in this band as spectrum is allocated to different users, whether that's cellular or wireless, or pretty much those two are the options. And so that's what we've been doing a lot of. We also want to test coexistence between new users in this band and incumbents in this band, or passive sensors in this band that may not be sort of specifically protected, but use the band, like radio astronomy. Telescopes use huge amounts of bandwidth because we need that for sensitivity. And honestly, most important, the goal of our experiments is to engage students in particular, but researchers at all levels, and have some fun. Like this can be fun. This could be a good time, and that's what we want from our experiments. Okay, so this is the VLA field experiment. How many of you attended the VLA field experiment last summer? Oh, I know there are more of you than that. Okay, so we went out to the middle of the desert in New Mexico, and we went to the VLA, which is that telescope there. It is a large interferometric telescope, and we emulated a 6G cell phone. Ask Ali for details on that. And we drove it around this telescope and looked at the effect on the telescope data, and also did some interesting sort of propagation stuff. Where could we see the signal, where could we not? Those of you that were there will know that we had some challenges with the maps, but we did get them mostly working by the end, and we had a successful experiment. As Frank said, these experiments are really good forcing functions to make sure our hardware and our software is ready to go and does the things that we want it to do. Sometimes that means fixing it a little bit on the fly, but so it goes in experiment land. So let's keep going. All right. So these are some of the pictures. I think we had a good time. No one got heat stroke, which was my primary concern. It was like 103, I think was the 104. Yeah, it was warm. It was toasty. We had to work a little hard to stay cool, but we managed. So you can see the transmit signal up in the corner there with the big chunk at the bottom is the 6G cell phone emulated signal, and the little beacons are up at the top. Frank mentioned those already as a sort of precursor to looking at coexistence beacons. You can see a mix of researchers and students working on the maps and then out in the field. It was a very successful campaign. We got a ton of data, I think all of which is in the SDS. Yes? Got everything? Yeah. And this was also data that was used for the student data competition. So it was a multifunctional experiment that provided a lot of value, I think, kind of across the flagship programs. And we did pick up the cell phone signal very strongly with the telescope because it's a very sensitive instrument, although with some interesting propagation effects that we probably still need to do some work on. And with the MEPs as well that were at different locations around the observatory. And as it says, we survived. That's important. Okay, so you heard the results of the student data competition. Hands up for participants. Okay, still a few of you still here. Hands up for the organizers. Yeah. So as I mentioned, we used the VLA data for the student data competition. I was really pleased with the number of participants in the competition. That was really great to see. So that is one way that we've been getting the experimental data out into the community and using it. All right, next was the Boulder Workshop. How many of you were at the Boulder Workshop in February? Yep, okay. Sort of. Halfway. So this was a fun collaboration, flash mob we called it, collaboration with NTIA. They have a transmitter, they turned it on, and MEPs were distributed into various cars, drove around, took measurements for the purpose of doing propagation studies. Frank, do you want to say anything more about this one?
Well, I'm 20 years behind on flash mobs, even if I'm 20 years ahead on radios. So it was a great experiment. We really pushed the capabilities. A lot of things were discovered and debugged that lead to more stability and better performance with UW-Madison in our summer experiment. So I think there's still a little bit of work to do redriving one of the routes that NTIA did for comparison. NTIA did an actual experiment that was very similar to this. And there's an aspect of duplication of that and then extension beyond what they did. So we had Chris Anderson helping us with this one.
Oh, I was just going to maybe add color commentary there. We're ready to go to rerun the data collect. We're waiting for NTIA to have money to turn the transmitter back on. So it's in their bucket to have a tech who can go take care of the transmitter.
Do they take Venmo? Can we just start a collection?
Yeah, I know. We can. Chris is working it. It's in progress.
Just kidding, NTA friends. So this was, I think, another workshop that really helped move some of the technical work forward, got the MEPs into yet a better state for data collection. I think there were still a few issues that were discovered, but those have since been addressed, which is a success. All right, I want to talk a little bit about Powder. We have a MEP deployed at Powder. And I think you had a little demo of that in the poster hall, right? Did any of you go say hi to Kirk and the Powder table at the poster session yesterday? Yeah. So this is our work towards integrating the MEP into an existing system with existing control. as well as other transmitters that we can listen to and do experiments with. So we're really excited that this has moved along, and the map is up on the roof now. Yes?
Yes, that's right.
Yes.
That's what the demo was showing yesterday, is measuring outdoors.
Yeah.
Oh, yeah, so the MEP was sitting up on the Merrill Engineering roof, and we had one of our radios up there, and then we were transmitting with some other radios a cellular signal that we're picking up on both. Sort of as a point of comparison between the two.
Yeah, and the maps were designed to spend time outside, closed up, of course. And so this is our first sort of long-term deployment is on the roof at Powder. And so far so good, right? More or less? That's great. So we can run experiments remote with that map, which is a capability that I think is really important for SpectrumX. All right, you heard from Ali yesterday, yes?
So Mary, I kind of wanted to maybe bring that point up for everybody so that, that map is at Powder. For anybody that's interested in running experiments, there's, plenty of opportunity to do that. The whole reason why we put it there was to make it a community resource. In addition to allowing us to run and test it and shake it out, and then the data from the map goes into the SDS. So, for anybody that has, thoughts on experiments to run that you might want to run, we've got the map there, we've got support from Kirk and Kobus on the Powder team, and then we have some folks who have engagement in the Powder platform and know how to set up and run experiments, and so we're trying to, let's say, up our game and get other people involved there. So encourage everybody to think about that.
Yeah, for sure. And if anybody has ideas for an experiment they'd like to run on that, you can get in touch with Kirk, with Scott, with me. If you like, you can join our experiment planning meetings. We do talk about the map there and do some logistics planning for experiments. So let me know if you're interested in that. All right, so the most recent experiment was 2 weeks ago. You heard about it from Ali yesterday. Raise your hand if you were at that experiment. Yeah? So this experiment was focused, yeah, you were there for sure. This experiment was focused on the potential interference between notional 6G cell phone and satellite downlink for a weather satellite in low Earth orbit. So our setup was a little bit different from some of the more mobile experiments, like the Colorado experiments. We had maps in fixed locations, and in one case actually hooked up to the device under test, which was the satellite downlink station. So we actually hooked a map up and got the IF off of that system, which we've done that locally, done that at Haystack. Yeah. Yeah, we've done that at Westford as well. So this is a capability of the maps that you can hook them up to somebody else's system and pull the data down yourself. We also had several maps up on a roof with a line of sight to the satellite station. And so those maps were, one was transmitting the 6G cell phone signal, and others were co-located to check the integrity of that signal locally. So I think what's the data count in SDS? I know it was 1.3 terabytes when we last spoke. Are we above that now? Live check. So, I mean, within a couple days of the conclusion of this experiment, we had 1.3 terabytes of data from it in the SDS. So we've come a long way in efficiency of getting data into the SDS. 1.9, almost 2 terabytes of data from this experiment that happened 2 weeks ago. It took us, I'm going to say longer than that, to get all the VLA data into the SDS. So, yes. So this was successful. We actually, honestly, I was surprised at how severely that signal interfered with the downlink, but it did actually make some of the downlink passes unusable for the folks running that system. So that's a really interesting insight that we already have, and more to come on that. Okay, so let's talk about what comes next. So from the beginning, we have talked about doing a capstone experiment to follow all of these other experiments that we have done. And what that means to me is that we involve all of the components of Flagship 1 in this experiment. So we're going to talk more about that. But the parameters for this experiment, we're going to be around Haystack Observatory, but not confined to Haystack Observatory. We have ideas for doing some propagation measurements in the sort of greater Boston, New England area, where we have a lot of interesting and varied terrain for fun propagation effects. But we'll be in the Northeast, we'll be based at Haystack, that's where our sort of home base will be. And we're again focused on the lower 7, that's the Flagship 1 area of interest. And we want to look again at the potential impacts of 6G wireless and potentially lower 7 Wi-Fi on real systems. Propagation is going to be a bigger part of this experiment than it has been in past experiments, so that'll be really fun. We have a complex environment, both at Haystack, where we have a lot of structures and other systems, including large radars at other frequencies. And the New England area also has interesting varied terrain to work with as well, including the ocean. We need to coordinate with other devices on site so we don't break anything, but that is something we're very familiar with and comfortable with at Haystack, and we'll make sure that this experiment does no harm to any other systems. And we're hoping that NTIA will have some participation in this experiment. We don't know yet. Hopefully we can get some feedback from them soon.
They have budget issues.
Yeah, so hopefully they'll be able to participate in some way, but TBD on that. Okay, so here's some outline of what I think we might do in this experiment. Tomorrow, first thing in the morning, we are going to have a planning session for this. So I'm going to go through my outline and the ideas that I have, but really tomorrow I want to hear from all of you. I want to hear how you want to test some of the things that you've been working on in your work elements. I have one brain, and it only has so many things in it, so I'd really like some input from others on interesting experimental work that we can do in this environment with the maps. So, building on past experiments, we want to center part of this experiment around protecting an incumbent asset, so a radio telescope and or a satellite downlink station. We can make our Westward telescope into both of those things, so we can use that as our incumbent to be protected. And in this experiment, we want to leverage the work that Ali has done on 6G cell phone signals, but we want to add to that some work with the beacons that the team at Northwestern has been doing with the beacons. We've chatted a little bit about what those experiments may look like, but we want to test reciprocity for beacons that are near but not exactly co-located with the sensor to be protected. That's one key component of the experiment. We also want to test the ability of these beacon systems to reduce problems for the incumbent system. That's their purpose, and we have an opportunity to try this out in a controlled environment, and so that's what we're going to aim for. We also want to do a little bit of comparison. There are different concepts of how to protect incumbent systems. Beacons are one, exclusion zones are another, ODS. Yes. Operational data sharing. Yes, ODS is yet another that the radio telescopes controlled by NRAO have been using. So we want to try some different approaches to protecting these systems and see what works well for the incumbent system, but also enables the entrant system, the cell phone, to have the most connectivity without causing problems for the incumbent. We would very much like to add an AIML detection capability to the work so that we can, in real time, autonomously detect interference on the incumbent system and do something about it. And finally, we would really like to include the phased array demonstrator to emulate like a cell phone base station and potentially do some beam steering away from the system to be protected. So that's you, Layla. And also we want to build on the propagation work that was done at the Boulder experiment, the flash mob with NTIA, and really expand the propagation measurements that we can do with the maps. This is something that we've been really interested in doing, and we've started to do some experiments along those lines, but this summer, using the environment that we have, both at Haystack and more broadly in New England, we want to try some fun propagation experiments with an active beacon and maps at various locations, both stationary and also moving in transit, maybe on boats, and go see the Cape. Troposcatter is something that a lot of folks are interested in, and so we're going to see if we can do some troposcatter experiments, maybe with afternoon thunderstorms, and see what effect that has. Let's see. Okay, so this is sort of the big picture. We're really interested this summer for this capstone in breaking down any remaining silos between the work elements so that all of these work elements and the components of Flagship 1 interact with each other. But all of that is centered around the goal of having a good team experience and a good learning experience for our summer students. So Haystack summer students, raise your hands. Okay. You are going to be front and center in this effort, and we're going to try to make it a fun experience as well as an educational one. And that goes for any other students that may be able to participate. Okay, yeah, I want to have time for questions, so we're good. What does that look like practically? I've talked about it a little bit already, but we've got sort of our data infrastructure that supports the experiments, and that has become a pretty well-oiled machine at this point. The maps, the data system, the interfaces, the metadata, that supports all of this work and is going to be really important for this experiment. We want to connect up some of these components that have been sort of developed in parallel independently. So as I mentioned, we want to have AI/ML detection to cause actions to happen both with the phased array demonstrator and also with the beacons. And we want to have potentially the beacons interact with the phased array demonstrator as well. So this is conceptual, and we're going to be talking about this tomorrow. So I'm going to send an email for the FP1 folks who hopefully will be participating, but bring your ideas, preferably in the form of a slide, for what you'd like to test, what you think will be ready, what you don't think will be ready, that's important too, and we'll talk about it, we'll make a plan.